So I'm Tim Pennings. I was at Hope College for 25 years, and now I've been chair of the math department at Davenport University for 10. And that's just come to an end. I'm going to do something else for the last little bit of my career. Wait and see what happens here. Anyway, this is as I was telling you, this is something I kind of thought of when I was down in New Orleans, and I looked down at the mighty Mississippi, and I saw them pushing barges up the Mississippi, and I got to thinking, what's the most economical way, energy efficient way of pushing them up the river? And so that's what led to this. And I thought maybe before going into all the details of that, I wanted to just tell students and whoever I give this talk to, why does math even work? Why does mathematical modeling even work? And this is a quote by Mario Livio, this is Scientific America, who basically asks these questions. Why are there physical laws of nature at all? And now how do I get to see all of my screen because the pictures are in the way? I don't know how to do that. So my part of my screen is blocked. But anyway, I think you can all see it. I truly don't know the answers, except to perhaps say that without these properties, life wouldn't have emerged and we wouldn't be here to ask the question. I've never liked that answer myself, but that was his. Do any of you know who said this? How can it be that mathematics, being the product of human thought, independent of experience, is so admirably adapted to objects of reality? Does that ring a bell? That was Einstein. How about this one? This is wonderful. Seems to be one of the fundamental features of nature. Fundamental physical laws are described in terms of mathematical theory of great beauty and power. You may wonder, why is nature constructed along these lines? One can only answer that our present knowledge seems to show that nature is so constructed. We simply have to accept it. One could perhaps describe the situation by saying the God's an astronomer, of a mathematician of a very high order, used advanced mathematics in constructing the universe. Isn't that a nice, rich thought? Anyone know who said that? That's Dirac. What was that one? How about this one? The book of nature is written in the language of mathematics. That's Galileo. Mathematics is replete with beauty and power. Its beauty resides in subtle pattern in the infinite. Its power mysteriously reveals order in the natural world. I said that. Thought I might as well throw that in. Here's another good one. Roger Penrose. I think this is wonderful. This is from, I forgot which book of his, but it's just a really nice way of thinking about this whole situation. He says you have the brain, the mind, and then you have these laws of nature, which can be written in terms of mathematical formulas, and then you have the material universe. And he explains there's three mysteries, really three mysteries. Why is it that the brain and the mind understands these laws of nature? How is it that we can that we even understand them? Then how is it that these more mathematical formulas can be used to describe this material world? A bunch of x's and thetas and so on a piece of paper describe the material universe. How is that? And then finally, how is it that this material universe makes up our mind and our thoughts and so on? So three mysteries. So anyway, that's kind of neat, I think. So that's just a little precursor to it. And then the other thing, before we get into the model, I just thought through what are the features of a good mathematical model. And so this is what I hope this model contains, and others should as well. It should require minimal and intuitive background required from other disciplines. You don't want something that's, requires a whole lot of knowledge of how blood flows or something or another before you can make sense of it. As much as possible, you want things out of their own experience. Secondly, they should be able to visualize it, again, kind of from their own experience. They can appreciate it and relate it to their own lives, both the question and the results. Here's important, that it provides insight and a conclusion that students would not get without mathematics. To have a model that basically just tells them something that they already would have said, yeah, of course, so that makes sense. That's what I would have guessed. Well, okay, there's some value to that, but much more is if it can give some insight that you wouldn't have gotten otherwise, especially if that's a surprising revelation. And finally, any good model should involve, this goes right back to what we were talking about, should involve asking students to list the assumptions and such. So I think that's it. So here's the model, and I've used this one now for years, and I use it in both my calc class, the first half of it, and then the whole thing, which requires differential equations, for the second half. And in calculus, I usually have it at the end of the semester and give them several days to work on it. And then differential equations, we take several days and make this a main project of the course. So you can see if you think it's worthwhile, but I like it. So here's the question: how much energy is needed, first of all, just to get a barge to cross a lake with no current? And so here's the assumptions. The energy needed is equal to the force times the direction. And so, or times the distance rather, force times the distance. So there's one property result from physics that they've probably seen even from high school. And then secondly, the primary, or we'll assume the only force acting on the barge is moving the barge through the water. So it's just due to friction with the water. And so that's either the dominant, or we can assume the only force acting on the barge. And I always make a point of saying, if you put your hand out of the window of a moving car, you can feel that the faster you're going, the more force there is acting on your hand. And I sometimes make a joke and say, yeah, I put my hand out of the Delta airliner that I was on last week when we were flying from New York to San Francisco, and it was a very strong force. The only problem is I'm no longer allowed to fly Delta Airlines. But anyway, that's the idea. So we're assuming that the force due to friction is proportional to the speed. So those are the only assumptions. And then let's see where we can go with that. So the first thing is that the energy then, if you multiply those together, just ends up being the constant times the velocity times p is your distance. And so if you want to minimize the energy, the distance and k, those are both set. So all you have to do is just make v as small as you want it to be. And there's basically, you can make it arbitrarily small. So there's your answer. You can get across the lake in epsilon total energy. So then I ask the question, why is this not realistic? And these are all part of the model. I'll send this to you, and then here's the type of answer that I'm hoping for. Customers can't wait an infinite time or even half that long to get their products. I had a student who just recently said the thing would rust by the time it got there. So the company would go bankrupt, something like that. So then, building the model, suppose more realistically that your company wants the barge to cross with a minimum cost rather than minimum energy, and let t be the time of travel. And so I ask them, why might the following be a good model for the cost? And answer is, well, two significant costs of transporting cargo would be the cost of the fuel, which is of course your energy, and then the time required. So ask them to kind of, again, hopefully see that that's not a bad model. What factors are important in determining the values of alpha and beta? And so alpha would be the cost of the fuel, efficiency of the engines. Beta would be the hourly wage for the employees, the number of employees on the barge would be factors there. And so once you have those, let's go ahead and find what's the minimum cost now in going across the lake with no current. So the distance is p, and your speed through the water is v. And so the time it takes you to go across is capital T. And so your cost then is going to be alpha times the energy, which was from what we had before, and then beta times the time. And so you want to minimize that. So you take the derivative, set it equal to 0, and you solve for V. And I like the answer because, as I say down below, I ask them, why is this physically reasonable? Well, you look at that and you say, oh, beta is the cost of time. If beta becomes larger, you're going to want to, your minimum, your optimal velocity is going to become larger. If time is valuable, then you're going to want to go at a greater speed. On the other hand, if the cost of energy, alpha, is large, then you're going to want to go at a slower speed. So it encourages them to look at the answer and to see that it does in fact make sense. So so that's that one. Then this is the interesting one. Now suppose that your company wants to minimize the energy needed to go upstream distance P along a straight portion of, I have it, the Grand River from Lake Makatawa to or whatever it was to Grand Rapids, where the current has a constant speed, V sub C is the speed of the current. And so there's a picture of it. Since the energy is required to push the barge through the water, the distance that you're going to need is not how far the barge moves along relative to the land, but how far it moves relative to the water. It's going through the water. So you're really needing now, when you want to figure out what the energy required is how much water is it passing. And so I call that effective distance. So the effective distance is basically the amount of water that it passes in going upstream from 0 to P. And this, I've just learned from experience, is the hardest part for students. It's the part that requires no calculus, anything else, just careful thinking. But this is a part that they struggle with. So we typically end up doing this as a class and kind of think through it together. So the first thing I ask them to do is I say, go ahead and figure out how much time it takes them to go from 0 to P. And the amount of time is going to be the distance along the bank, which is P, divided by their speed upriver. And the speed upriver is the speed that they're going through the water, that's V, minus the speed of the current. So you take distance divided by their effective speed going upstream, and P divided by that is the amount of time. Once they have the time, I think you can see my cursor here, once they have that time, then they can multiply that time by just the speed with which they're going through the water all the time, their velocity through the water. So there's their velocity through the water times the amount of time that they're actually in the river, and you multiply those together, and there's your effective distance. That's basically how much water you've passed as you've gone from 0 to P. Okay, so stop me if you have any questions on this, by the way, if anything doesn't make sense. So now that you have that, then what's the energy? And so your energy is going to be the force times that effective distance. And so your force is, again, just proportional to your speed through the water. And you multiply that by your effective distance, the amount of water that you've passed, and you get yourself a pretty nice, it's just right for Calc 1. Just the right level of difficulty to challenge them, but be hopefully very doable. So you want to minimize that. And so you minimize it, obviously, by taking the derivative, setting it equal to 0. Again, my students sometimes need help, just reminding them that it's your numerator that you want to set equal to 0. Do a little bit of factoring. Just, again, to me, it's just the right amount of work. And you pull this out, and you have two options. V is equal to 0, which doesn't make sense because you'd be going backwards. And then the other one is twice the speed of the current. And how neat is that? So so if you think about it, I tell the students that if I'm kayaking upstream in my kayak or canoe, and I want to go upstream to get to a certain destination with the minimum amount of energy, then I want to be moving upstream at the same rate at which I see the water going downstream, right? Because it's going downstream with velocity VC, and I'm moving through the water with velocity 2 VC. So I'm heading upstream then along the bank with a velocity the same as what the current is doing. So it's kind of nice. I mean, a very nice natural answer there. it takes into account two things. Well, we'll get into that. So if the barge is going at, if the water is going at 3 miles an hour, then the barge should be going at 6. And again, it seems to me that this is probably a pretty reasonable answer. Those were decent assumptions that we had. So then I ask them, go ahead and graph this thing and interpret the graph. And so here's the graph of the energy. This is assuming that the speed of the current is 3. So notice right here at 6 is your minimum point right there. And then notice that as you move away from 6, if you go faster than 6, your energy increases rather slowly. But if you decrease from 6, you reach an asymptote as you approach 3. And I asked them, why is this? And again, it's just a great question to get them to really wrestle with what's going on here. And oops, I haven't used Decimus for this. And so explain, why is it that it goes up so quickly for values of V that are slower than the speed of the current, than twice the speed of the current? And I say, actually, this answer is best read if you start here. It makes sense, because if you're just going a little bit faster than 3, let's go backwards here. If you're just going a little bit faster than 3, then you are spending a long time getting from one space to another. And so asymptotically, as you get closer and closer to 3, you're spending an infinite amount of time in that water. And all the time in the water, you're going at least 3 miles an hour. So it's very inefficient to go barely faster than 3 miles an hour. If you go at 3.0001, you're going to be in that water a long time making your way upstream. So so that's the key there, that you can help them see. And I always explain that this is why, if you're caught in a rip current in Lake Michigan or an ocean or something like that, the advice is never to try to swim against it. You always swim perpendicular to it until you get out of it, and then you swim toward shore. But if you try to swim against the current coming in toward shore, this is what's going to be happening to you. You're going to be spending a lot of energy as you go just a little bit faster than the rip current. So a lot of nice kind of natural life advice from this. So anyway, there you are. So if you just go barely faster than 3, you're spending a lot of energy to get upstream. So then put these two together, and now let's look at the cost of going upstream against a current. So the same thing as before. E is your energy, T is your time, and beta is going to be the cost of the wages and so on, and this is going to be the cost of the energy. And you do the same thing as before. This, although now this is your energy that we had from part 3. And the time is, again, your distance divided by your speed going along the bank. And so you combine those together and you get this. And again, for me, I think it's just the right amount of algebra. It's a nice algebra problem. Take the derivative, set it equal to 0. You want the numerator to be 0. They have to use a quadratic formula for this. A really nice example of using the quadratic formula, because they're used to just numbers. And here they have to see that this is your A and this is your B and this is your C, or this is your C right here. So this opens the door when they realize that this is a quadratic formula here, a quadratic equation. And so they get all this. Then to get students to realize that I can divide the numerator by the denominator, that's the tough one for them. And you get a much nicer answer than this one. It just comes to this. And now you look at that and you say, oh, why does that make sense? Well, first of all, notice that if beta is 0, which means there's no cost of time, then you're just going to get VC plus VC, 2VC, which is the same answer as you had before, which is what you would have expected. And secondly, notice that this beta over alpha k is the same relationship that we had in the earlier problem. As beta increases, if the cost of the time increases, then you want to go, your optimal speed is faster. If the cost of the energy, alpha, increases, then this optimal speed is going to be slower. So again, you ask them to think through all that and explain why this isn't a reasonable answer. So there's that one. So that's where I stop if it's a Calc 1 problem. So I throw in one last question at the end, basically, how can you improve the model? But this is a nice Calc 1 project for the end of a Calc 1 course. So then if they've had differential equations, then I go on to this one. The previous model explored the case of traveling upstream against a current of constant speed. More realistically, the speed of the current may change as the river widens or narrows, and as you maybe add water to it from tributaries or whatever. And so now we're going to assume traveling upspeed against a variable current, where we express the speed of the current as, again, I can't see it, but it's VC, where V sub C is the speed of the current at point X along the river, along the bank of the river. And we'll always assume that you go at least as fast as the speed of the current, so that you're always making headway. You're never getting pulled backwards. So the same thing as before. Your total energy is going to be the force due to friction, which is proportional to your speed through the water, times your effective distance. And your effective distance, same as before, is just your velocity through the water times the amount of time. What's different is that the amount of time it takes, we can't just take the distance divided by the rate anymore, because it's variable. And so we're going to have to use a differential equation in order to get it. Whoops, I went backwards there. So I give them a hint. I say express your speed along the bank, dx dt, in terms of v and the speed of the boat through the water and the speed of the current, and then use that to find your total time. So give them a little hint. And here's the work. Here's your speed along the current. That's your speed through the water minus the speed of the current, which is coming at you. Separate the variables and integrate, and you're going to get the total time is equal to the integral of this as you go from 0 to p. And so there's your time. Now that you have your time, you can just put that in right here, and you get kv squared times your time. So there's your general formula. So then I say, okay, let's take a specific example. Let's assume that your speed is varying linearly, that it just keeps going faster and faster as you go along the river from point 0 to point P. And so it's growing as a function equal to alpha times x. And so given that, I say express this in terms of v and this and so on. And so here it is. Oh, here's what we had before. We had that before. Oh, dang it. Here we go. Oh, sorry. There it is. Okay. So you got all this. You take the antiderivative of this, of course, you get the natural logarithm. And there's your natural logarithm. Stick in 0 and p. And you get your kv squared times that right there. Again, I like it because it's all doable. It reminds them of things that they either should know or hopefully do know. And then they can use a property of logarithms to write it like this. And then again, I give them a little hint to just help them from there. So now there's our energy. Now we want to take the derivative and set it equal to 0. We want to find the minimum. So you take the derivative, set it equal to 0, and you're going to get this right here and that right there. Won't go through the details, but just standard taking the derivative. And then I give them a little hint up here. I say, notice that you have this quantity v over, is that a v or a nu? I guess I'll call it a v. V over v minus alpha p. You get that both right here and right there. So I just say, go ahead and call that beta. And then you can write this thing more simply like that. They can kind of see the form of it. And once they see the form of it, they notice that one root of that makes it 0 is just when beta is equal to 1. 1 minus 1 plus 2 times 0 is 0. So that's one root. But then the other root you can get by using Decimus and just taking the graph of this thing, putting it into Decimus, and finding the value of beta that makes that 0. So it's just, again, I like it, just the right amount of technology. They're going to have to use it. They don't use the technology for the whole problem, but they do need it right there. And so they can find the beta that makes that, solves that is this value right there. Now that you have beta, you just go back and you can find your value of V. And so you set that equal and you solve it for V, just a little bit of algebra. And you get V is equal to about 1.4 times alpha times the value of P. So there it is in terms of both of those parameters. So now if alpha is equal to 1/5 and it's a 10-mile trip up the river, then you're going to get an answer of 2.796 miles per hour. So in other words, if you're in a boat and you want to just set the engine at a certain rate, which is going to go up the river 10 miles, and you're not going to vary the speed of the engine, you're just going to set it at that given rate. This would be the rate to set it at, so that you get upstream against this variable current with the minimum energy. And so then I ask them this final question. I say, okay, this is a 10-mile trip upriver, and the river, the speed of the river increases uniformly. Since alpha was 1/5, the speed of the river is going to increase uniformly from 0 to 2 miles an hour as a function of position. It's going to vary from 0 to 2. And so the current has an average speed of 1 mile an hour. Okay, it varies from 0 to 2 as a function of x. So the average speed as a function of x is 1. So I just ask them, I say, recall from what we did before, that the minimum energy, or I should say the optimal velocity was when you went at twice the speed of the current. So given that the average speed of the current is 1, wouldn't it seem reasonable that we should have gotten 2 as our optimal speed, since the average speed of the current was 1, that we would double that and go at twice the average speed? And I say, explain why it ended up being almost 3 rather than 2. And then I hope that they give me an answer kind of like this. The required energy increases much more quickly as you decrease, as our graphs showed, from twice the velocity than when it increased. So it's better to err on the side of going too large than too small. And so again, it goes back to that previous problem, and it gets them to really think about the previous one. And then I also say, by the way, if you do go at 2, you're never going to finally get to the out of the mouth. You're going to asymptotically go to 0 as you get to the mouth of the river. So there's another part of it. So so finally, then I say, how can you make it more realistic? And my own answers are, we're assuming the mass of the barge stays constant, but as you use the gas, it's going to actually lessen a little bit as we go. We're assuming the energy efficiency of the engine is independent of the speed of the engine, and that's probably not the case. So you can kind of take it from there, and students will come up with other assumptions as well. So I think that's it. Let me see. Yep. So there's my. If you're interested in this, by the way, there is an article form of this that appeared in Math Horizons back in I forgot what it was, 2010 or 12 or something like that, and it's just called barging ahead, optimizing a trip upriver. So if you want to find kind of everything all explained and written out, either for yourself or your students, just go to Math Horizons and check it out. But I can give you basically the same thing you saw there without the answers. That I can give you either the text, the tech file, or the PDF, and you can alter it if you want to, but use it for your classes. As I say, I've been using it for years, and I like the things that come out of it. So Yeah, sorry, I didn't ask for any questions kind of as we went. Any thoughts or questions?
So this may be too hard, but you could have the ship's velocity change as it goes upstream. I guess it becomes a sort of variation, calculus of variations problem.
Yes. And what would I've thought about that. Do you agree with this? That if you could have the velocity of the boat change, that the optimal would always be to just be going at every point in time at twice the speed of the current at that point? It seems reasonable to me. You always have to be a little nervous when you make those reasonable assumptions, but that's
Yeah, I don't know that either, but that I wouldn't be surprised if that was the answer that one would derive.
it seems like it would, just by doing kind of a differential form of it, that's what it
Yeah,
would be.
the
But
same way you
yeah,
kind of do
yep, and
snow fog.
that's actually kind of, yeah, exactly. It'd be a nice question to ask. Actually, that's a very nice question. That's one I should include in here. Is very just get the students thinking about that.
Thank you.
Yes, very good.
Thank you. Really good talk.
Okay, yeah, thank you. Thanks for coming, everyone.